Welcome to solverfy.
Hey everyone, this is question number 54 from chapter 31. Okay, so in this problem, we are asked to consider a system of nuclear power plants that produce 2100 megawatts. Megawatts of power. Okay, part A asks us what the total mass of 23592 uranium the mass of 23592 uranium fuel would be required to operate the plant for 1 year. If, assuming that 200 mega electron volts is released per fission. Per fission. All right, and this is part A, is finding what mass we need. Okay, so this is pretty much just to start this question, pretty much just a basic equation. So we need to find the number of nuclei of uranium needed, and then we can find a mass. So that is going to be the number of nuclei is equal to the power times the time divided by the energy per fission. Okay, so our fission is given in 200 mega electron volts. First things first, we actually need to convert that to joules because we're given a power in watts. So we can go ahead and start that. So 200 mega electron volts is 1.6 times 10 to the minus 13th joules. Okay, and that gives us 3.2 times 10 to the negative 11 joules. Okay, so now we can start solving everything, putting into this, solving the equation, putting all the variables in now that we have this E in the proper form. Okay, so I'm going to remind you of our equation. N equals power times time divided by the energy for a fission. And we're going to pretty much just plug and chug. So we have 2100 megawatts. Our time is 1 year, which we will have to convert to seconds because watts is joules per second. And then 3.2, which we just solved for, times 10 to the minus 11 joules. Okay. So expanding on this now, we need to do that conversion from megawatts to watts and then years to seconds. So we have equal to 2100 megawatts. We gotta go 10 to the 6th for mega, joules per second. That's equal to 1 megawatt. And then seconds in a year, 3.153 times 10 to the 7th seconds in 1 year. And that is times 1 year. That's your very long numerator with all of our conversions. And then divide again still by 3.2 times 10 to the minus 11th joules. Okay, when you plug that into your calculator, you get 2.07 times 10 to the 27th fissions. And I'm just going to abbreviate with FIS. So to put this into a more familiar form, we can do the required number of nuclei for 1 year is that 2.07 times 10 to the 27th. And then we have the mass of uranium is 235. So we have 4.0 times 10 to the minus 25th kilograms per fission. We can find the total mass required. So the mass of uranium 235, we're just going to take this number of fissions and multiply by the mass, which is 4 times 10 to the minus 25th kilograms per fission. And that gives us 830 kilograms. So that is your mass needed to run this reactor or power plants for 1 year. So now we can move on to part B, which asks a little bit wordier. Typically, 6% of the uranium nuclei that undergoes fission produces strontium, which is a beta emitter with a half-life of 29 years. Okay. What is the total radioactivity of the 9038 strontium? In curies produced in 1 year. So curie CI in 1 year. All right, so once again, this is just an equation that you should familiarize yourself from, that we're going to plug in knowledge to. So the expression for the activity of a radioactive sample in terms of number of radioactive nuclei is R equals 0.693 divided by time of the half-life times N, which is the number of radioactive nuclei. So we have 6% for the number of nuclei. We have the number of nuclei. We solved for that in the beginning. So this becomes R equals 0.693. Our half-life is given 29 years. Our number of radioactive nuclei we solved for in the first part of this question, which was 2.07 times 10 to the 27th, but we're told in the question stem that it's 6%. So that becomes 0.06. Okay. And again, we need to do a conversion, which I am just going to tack on to the end of this. Again, we're doing seconds to years because this is in years. We need to change it to seconds. So we have 1 year, 3.153 times 10 to 7 seconds. And that is our conversion. Okay, so when you multiply all of that out, you get 9.4 times 10 to the 16th decays per second. And we are asked to give it in curies, so we need to convert. My pen is acting a little weird, I apologize. Okay, so we're converting to curies, and 1 curie is equal to 3.7 times 10 to the 10th decays per second. I'm just going to put DEC. All right, and divide that out, and we get 2.54 times 10 to the 6th curies. And that is your answer for part B. Hope this helps.